Welcome everyone to the March 2021 meeting of the Memphis Astronomical Society. I'm your host, Jeremy Veldman, and we got a program for you tonight. We've got Jed Cowell of Cummins Engines and co-owner of Black Ice Cooling right here in Memphis, who's going to be helping us overcome some misconceptions about time dilation. And Einstein wrong? Interesting. So be sure you stick around for that. We've got a very informative program for you tonight, a lot of great information. And this is going to be a content-rich presentation for you. But before we get started, just a few preliminaries. I'm going to go ahead and share my screen right now. First of all, welcome everyone. Thanks for taking the time to join us. All right. So again, we are the Memphis Astronomical Society, and we are a nonprofit public service organization promoting interest in education in astronomy and related sciences. Our website is memphisastro.org. And of course, you can find us online. We're on social media. We have a Facebook group. We have a Twitter account. And of course, take a minute if you haven't already to subscribe to this YouTube channel. Want to pay a special shout out to the now 1,700 plus subscribers. Thanks again for subscribing to this channel. Hope you get a lot of value out of tonight's meeting, as well as the other meetings that we've got coming up and the other presentations we've got coming up. So take a minute to subscribe and hit the notification bell to be notified of future videos as we post them to this channel. Now, our website, of course, is memphisastro.org. And I want to give a special shout out tonight to Mr. Steve Wright, Mr. Wright, who gave our website an overhaul recently. So we've got a new look, and I want to point out a couple things. So again, the URL is the same, of course, memphisastro.org. If you are interested in joining the Memphis Astronomical Society as a future member, you can do that right here on our website. There's actually two places. You just click on the join button on the right or in the upper right next to the search bar. It will take you to this join form, and you can just fill out your details there. Several of you have already done this, and we've got your information. We are going to be working to streamline the membership approval process more quickly going forward, and removing some of the barriers / obstacles and making it more seamless, if you will. So thank you again, Steve. Excellent look to the website for helping us get a new look and a new platform. He's going to be working on some of the other platforms as well, and really helping us get more consistent with our branding. So check that out, memphisastro.org. Now, you can also join our email list by going to this link right here, joinmas.com, and just enter your name and your email. If you're not on our email list already, please, feel free to do that at any time. We send notifications out about once a week regarding upcoming events, whether it's meetings like this one or observing sessions, whether it's virtual events like we're doing right now, or eventually as we wind down COVID, we get back to more outreach events that we're looking to start doing again as the year progresses. So go to joinmas.com, enter your details if you'd like to be added to our email list. Now, calendar of events, not much is changed. However, we are getting toward the end of COVID. Now, it's been a year now since we've been shut down, and we've done all these meetings virtual. I'm very happy and very proud, quite frankly, of the work that we've done collectively to keep the ball rolling throughout the past year, as we've had to make adjustments due to these unprecedented times. I realize it's somewhat controversial. Not everyone is in agreement as to the severity of the nature of this, but we've done our best, I think, to abide by the guidelines, and then also to kind of go with the pack, if you will, for all the other organizations out there. Having said that, there is a vaccine. Many of us have already gotten it or are in the process of getting it. So we're nearing the end here. And the question is coming, when are we going to get back to live meetings? And I will attempt to answer that in just a moment. Now, our calendar of events, tomorrow night looks pretty good. Right now it's cloudy, but if the weather clears up as it's forecast to do, there is the possibility that we could have favorable conditions for the first time in quite a while, quite frankly, for an observing session. So if you're on our email list, please keep an eye on that, because we may, in fact, open things up to a bring your own equipment observing session tomorrow night. So if you have a telescope, haven't been out for a while, and we've been cooped up for quite a while, survived a winter storm a couple of weeks ago. So tomorrow night looks pretty good. And of course, ironically enough, March is the Messier Marathon month. We made a big deal out of this the past 3 or 4 years and had just horrible weather every time we tried to plan one. This year, we didn't do that. And now we've got potentially a great night. So that's just the way the cloud gods roll. We just got to go with it. But if you want to do a last minute Messier Marathon, tomorrow night might be a good night for it. So keep an eye on your email for that. Now, next week, we have another virtual star party, and these are hosted by the Dyer Observatory, Vanderbilt University. MAS is a participant along with other astronomical societies and organizations throughout the state of Tennessee. We've been doing these now for the past 7 or 8 months. And Bays Mountain Planetarium is a participant, as along with the Barnard Seaford Astronomical Society. So next week, I don't know. We got rain coming. We'll see. But if the skies are not clear, we're going to do this anyway. It's a combination of live observing via Zoom, of course, and other topics in astronomy. Very informative. And we'll be sending a link out to this as well. So that's next Saturday, March the 13th, another Tennessee statewide virtual star party. And we're trying to get more people to participate in this so that you don't hear from the same 4 or 5 people, every time. So yeah, make sure you mark your calendars for that. That's 7 p.m. Central next Saturday, March the 13th. Okay, new members. I want to take a moment to recognize Ilya Green, and your application was received about a month ago, and we officially approved your application at the February 12th board meeting. And I'm going to go ahead and take a moment to see if she's actually on the call tonight, because I want to recognize you and say thank you for joining our group. If you are on live tonight via Zoom, just take a minute to say hello, and so we can acknowledge you. I'll pause now. Well, excellent. That upholds a long-standing tradition of the participant, the person who's recently approved as a new member, of not actually attending the next meeting. So I'm glad that tradition continues. But regardless, thank you. Welcome. We're very happy to have you as a new member. And for those of you who are interested in becoming members, I will have a link to a membership application in the description below this video. I'll show you that in just a moment. Now, when you become a member, one of the benefits is you get access to our newsletter, which is the Meteorite. And it's got some great content in there, such as articles, minutes from past board meetings, an astrophotography gallery, and then also a sky chart for the month. And be sure you check out the article in this past month's edition, March, of the Meteorite. Longtime member Bill Bustler had some things to share about astronomy over the past 50 or 60 years and some of the changes. So be sure you check that out. In addition, we've added a news segment to the Meteorite, kind of an astro news segment. And we're kind of developing this as we go also, just to add more content to it. And of course, February has been a very interesting month in the world of astronomy. A lot of things have happened. Primarily, the Perseverance probe safely touched down on the surface of Mars after being launched 7 months earlier. And I love this image. It's just iconic. You can actually see a live shot from the camera as the rover is descending to the surface of the planet from the probe after the retro rockets were fired. And then the sky crane is slowly lowering it down. I was thinking about this earlier. The person who actually conceived of this idea for landing a probe, a rover, if you will, on the surface of Mars has got to be certifiably insane. This has got to be the craziest, stupidest, most remarkable idea I think I've ever seen. And it's worked twice. Curiosity and now Perseverance. Just absolutely phenomenal. This person should have their head examined and should be in a mental institution for coming up with this idea. And the fact that it worked and has worked perfectly twice is just remarkable. Just an absolute incredible feat of engineering. Fantastic, fascinating. I mean that with all respect. The fact that we can land on the surface of Mars like this with this kind of technology it just shows you how fantastically fortunate we are to live in these times. And so this is groundbreaking, literally, and it will be really interesting and fascinating to see the discoveries and the developments that come from Perseverance, much like Curiosity and its predecessors, as we continue to explore the surface of Mars. So love this shot of the sky crane lowering Perseverance to the surface. And again, I just can't say enough about what a remarkable accomplishment this is for everyone involved in this project, and how fortunate we are to be alive to witness this. So this is fantastic. This is really great. Okay, in addition, we also have an astrophotography focus group meeting that we're starting to do monthly now. This is toward the end of the month, around the time of the full moon, when, of course, observing conditions are not as favorable. So we'll be sending another notice out regarding this toward the end of the month. So keep an eye on your email for that as well. So it doesn't matter what level you're at, whether you're experienced or brand new and just looking to get into this hobby. The primary objective of this group is to match up the teachers with the learners, and then to kind of get a mentoring program going. So the last meeting was very content rich. We kind of did a comparison of PixInsight versus Photoshop. And several of the guys who've been at this hobby for years sort of shared their process for image processing. So it's going to be very interesting to see how this develops over time as well. So if you are interested in attending the next meeting, again, we're doing this via Zoom. Again, keep an eye on your email. If you're not on our email list already, just go to joinmas.com, and we'll send out an email notice about this sometime within the next week or two. And it's toward the end of the month, right around the time of the full moon. We do this on a Saturday night. So
Jeremy, the next meeting is the 27th, 7 p.m. And the preliminary topic of the evening will be auto guiding.
Excellent. Auto guiding.
And whatever else we come up with, but that's what's on the agenda for now.
Fantastic. Yeah, there's a lot of content, of course, and a lot of ideas for the hobby of astrophotography. So I have a feeling that you're not going to have a hard time coming up with either presenters or topic ideas for these meetings in the near future. So, okay, so that would be March 27th at 7 p.m., correct?
That's correct.
Okay, that's the next meeting. All right, excellent. So for everyone tonight, I will have links to these two documents in the description below. And that, of course, is the March sky chart, as well as a membership application. Now, another way that you can become a member is to just download this membership application, fill it out. All the fields are already pre-filled, so you just type it in the PDF file, and then email it back to us at info@memphisastro.org. So there's really two ways that you can sign up to become a member. You can do it on our website, memphisastro.org. Just click the join button, or you can download this membership application, fill it out, and then email it back to us at info@memphisastro.org. So yeah, be sure you check out those two documents. I'll have them again in the description below when we post this video to our YouTube channel. Okay, like I said before, COVID is coming to an end. We're seeing the light at the end of the tunnel. Of course, this is ongoing and has been now for a year. And the $1 million question is, when are we going to get back to live meetings? And we're still discussing this. The next few are going to be virtual. However, we are planning an event in July, and we're going to show a film called Luminous. It's a documentary from a professor in Western Michigan, not too far from where I grew up, interestingly enough, who is attempting to predict a supernova. And the plan is to show the 90-minute version of that video for our July meeting. That would be, I believe, the second Friday in July, because the first Friday is usually around the 4th. So the idea is, by that time, 3 months from now, 4 months from now, most of us, if not all of us, hopefully will have been vaccinated. COVID should be in the rearview mirror. And we're even discussing the possibility of renting a theater and showing this film in the theater, and then also having a Q&A session afterwards. It's still preliminary, but to kind of wrap up the introduction to the meeting, I thought I would show you a quick intro clip to what's coming up in July and our plans to reopen around that time. Rick, did you have any comments? Okay. So let me go ahead and show that, and hopefully you guys can hear the sound. So I'm going to show that to you right now.
After hundreds of years of everybody knowing about exploding stars, knowing that there could be new stars in the sky, nobody has ever been able to predict this.
A nova, a new star. That's what Larry Molnar is looking for.
1 in 10 million stars would go through this in a human lifetime.
It's much beyond a needle in a haystack. A needle at least looks different from the rest of the hay.
If you think about who out there is going to discover this star that's about to explode, Larry's not the most probable suspect.
My job is to get the students interested in science. Doesn't matter if we discover something big or if we discover something that turns out to be wrong.
He is deeply curious, someone who has that raw, just hunger to understand the cosmos.
If we see this star blow up, we're going to see what happened 1,000 years ago with our modern cameras.
Wow, this is just a few years away. Nobody's ever seen anything of this kind.
So suddenly we realize we're on a timeline here.
In 2022, we might be able to witness an explosive creation of a new star visible by the naked eye.
I think it takes a good deal of courage to step out there in front of other scientists who are going to do everything to essentially shoot it full of holes.
I still think that there are other explanations.
We don't think it's going to emerge.
I'm skeptical. I think it's a bold prediction.
Most predictions fail. If you make a really risky prediction that then fails, you lose everything.
It is extremely risky, can be very painful. You may waste all your life trying to understand something, and at the end of the day, you really realize that you don't get it.
Larry's working at the edge of knowledge. It's scary out there on the edge.
Okay, so again, we are planning to show that in July, second Friday in July for our July meeting. And that is more or less unofficially when we're planning to transition. Can everybody hear me all right?
Yeah, Jeremy, sorry about that. That was actually my mistake.
Okay. All right. I'm gonna go ahead and share one more time here. Okay, with that, I would like to transition to our main program tonight. And of course, the topic of time travel and or time dilation has been a fascinating one and an intriguing one for all of us who have either studied science or taken a physics class, a modern physics class. And tonight's presenter has got some interesting ideas to share that should stretch your thinking a little bit. Now, at this point in time, I would like to turn the meeting over to Steve Wright. Steve, of course, is one of our board members. He knows our presenter tonight, made the introduction to our group. So I would like to officially turn it over to him at this point to do the honors of introducing our presenter for tonight. So Steve, take it away.
Thank you, Jeremy. Good evening, everyone. My name is Steve Wright, and I am one of the newest members of the Memphis Astronomical Society. And I reached out to the members of the board about a potential speaker. He was a shady person I know who's selling this crazy idea about time dilation from the trunk of his car. Anyways, to my surprise, the board thought this would be very interesting. But maybe I presented the speaker in a more polished, professional way. Our speaker today is Jed Cowell. He's a highly successful businessman who is now currently, wait for it, Director of Global Warehouse Operations Excellence for Cummins Engine Company. But that's not why he's here. Jed is like all of us. He has a passion for physics and a passion for astronomy, and he's especially interested in time dilation, and he has a new twist. I heard about his theory a few years ago during what was supposed to be a marketing meeting, and it turned out for the hour we talked about time and space instead. Jed put something in the back of my mind that day. This idea of his is out of the box, smart, and innovative. This idea should get out to the public for review, and let's see what happens. So here he is. May I present Jed Cowell, who will talk about a new way to understand time dilation. And Jed, can you take the screen?
Yes, I can. Thank you very much, Steve, for that wonderful introduction. I really appreciate that. And so let me do a screen share real quick, and you guys confirm that you can see what I have there on my screen.
Yes, we can see it.
Okay. All right, very good. And I want to first thank Steve for the support he did in presenting this material here. Steve helped with the graphics. He and his daughter did a fantastic job. You can see from this very first graphic here, that's quite an interesting way to present time. Excuse me. So before I give more details about who I am and more details about how I got here, let me quickly calibrate you on exactly what we're talking about, because time dilation has a lot of dimensions to it. We were talking about the time dilation mentioned by Albert Einstein in special relativity, 1905, and we're focusing on velocity. Okay, 10 years later, Einstein incorporated many of these concepts into general relativity, which was involving gravity. Okay, we won't be talking about gravity tonight, just on the velocity piece. Okay, now, for some of you, I've only been speaking for maybe a minute, and some of you have already had a time travel experience. What I mean by that is, this is a physics discussion, and you were transported back in time to your days of college where you signed up for an astronomy class only to find yourself in a physics class accidentally. And instead of these beautiful planets flying around in your head, there's equations flying around in your head. And you felt that a feeling of nausea come up upon you. Well, let me put you at rest here, because there's only one equation in this presentation, and the presentation is only 18 slides long. Okay, so now we'll use that equation creatively in a few different ways, and you'll see, I think, some dimensions of this that you most likely haven't seen before. But what I hope you get out of this is that you understand a lot more about time dilation, and that's number one. Number two is that you understand exactly how did Einstein get to the point where he made this declaration or this discovery there. You don't really find that piece of it in many of the writings or teachings. They tell you what happened, but not exactly how he got there. So this is my opinion from the research I did on how he got there. And then also I'll present an alternate theory about time dilation, along with some problems that led me to think that there might be a problem with the theory. Okay, so my name is Jed Cowell, again, amateur physicist. I was a Memphis resident for 32 years. I currently live in Columbus, Indiana. And while Indiana is a wonderful place to live, Memphis is considered our home, okay? I've been married 36 years. I've got 2 grown kids and 2 grandchildren living there in Memphis, and 1 grown child and 4 grandkids in Indiana. I am a U of M grad, go Tigers, undergrad in MIS, and a graduate degree in finance. And then, as Steve mentioned earlier, I work for Cummins. And basically what I do is our global service parts warehouses, I do engineered material flow to design how material flows in and out of our buildings there. So while I have very few impressive credentials, my most impressive credential is obviously that I'm a longtime friend of Steve Wright. Now, I won't ask for a show of hands on Zoom as to who agrees that that's an impressive credential. We'll just assume that everybody's in agreement on that. Okay, so let's dive into the agenda with that background here. But before I go right into the time element of what I want to talk about here, I want to briefly remind you of the kinship between physics and astronomy and the importance of time. Okay, then we'll talk about a brief review of the special relativity and time dilation concept, a little more detail. Go into what's probably everybody's favorite aspect of time dilation, the twin paradox. It's very fascinating, but really kind of hard to understand how that could be true. We'll then look at the experimental verification of time dilation. Okay, so the first four elements I'm going through are building the case for time dilation as we understand it from special relativity. But then I'm going to shift gears a bit and talk about some problems that are evident in the theory itself that I've come across as I tried to understand it. And then I'll introduce an alternate theory that I have about atomic dilation. And the last thing I'll say before I go to dive into the topic here is that the reason I got into this was not because I was searching for an error in special relativity or even ever dreamed that there would be a problem with it. I just simply wanted to understand it. It was just so fascinating to me that, the question was, how can time warp? It just didn't settle well with me. And so I said, okay, let me go research and let me learn how it does. Okay, so that's how I got here. So first, the kinship between physics and astronomy. If you ask a bunch of people, which is more stunning, the rings of Saturn or the Lorentz factor equation, let's be real, okay? They're going to choose the rings of Saturn. That's just kind of the way it is. And while astronomy is clearly the more glamorous area of study, equations can be beautiful too. Okay, and many people have a hard time understanding how that could possibly be. But when you understand what's behind an equation, you can see a lot more beauty there. And to me, I love astronomy too. And I take my grandkids out and we look at, whenever there's a astronomical event that we can see with our tools, we try to celebrate and go out there and explore the universe. But I think you're going to see a little bit of beauty in an equation, this very small equation we have here that we'll talk about later. So anyway, it's about relativity tonight we're talking about. So beauty is in the eye of the beholder. And thank goodness we have people that love to explore the rings of Saturn, and we have people that love to explore the Lorentz factor equation. Okay. So also, in addition to a kinship between the two, astronomy and physics are complementary in many, many ways. Three examples I have to demonstrate that are quite familiar to all of you, but I'll just remind you of those. Astronomy, for example, discovered the orbital precession of Mercury, Leverrier, mid-1800s. Well, sometime later, physics came along and confirmed it and explained why. And this was Einstein in general relativity, 1915. Second example is physics predicted the bending of light near massive objects. That again was Einstein in general relativity in 1915. This time astronomy came back and confirmed it. Arthur Eddington, solar eclipse, 1919. And then the third example is physics indicated a static universe. Well, this was when Einstein was creating an equation to explain the stability of the universe. Is it expanding, contracting? Is it static? And he introduced the cosmological constant. And that was in 1917. Well, everybody's aware that astronomy came along later and said, well, wait a second, Mr. Einstein, we may have an expanding universe here. And that was, of course, Edwin Hubble in 1929, one of the most famous astronomical discoveries ever. So physics and astronomy have worked together for, eons. And astronomers knowing a bit about physics can be very helpful as you explore your domain. And the same thing is true in reverse. People interested in physics, the more we know about astronomy, the more we can do our job well. And the exploding star thing that Jeremy introduced earlier was quite fascinating to me too. So the two disciplines tend to work together quite well. Okay, with that background, we're now going to transition and start getting into a little more depth of theory here around time dilation. So before we get in directly to it, however, let me talk about a few of the problems that led up to special relativity and the time dilation discovery that Einstein came up with. I'm not going to go into detail on any of these. I'm just going to mention them briefly. Most of you will be familiar with the concept, and they really don't matter too much until we get down to the bottom of the list here. So the first one is the question, is space empty? or is it made up of something? Let's call it ether. That's a question that cavemen probably had, and we certainly still have. So physicists were wrestling with that, and astronomers were too. Back in a few hundred years ago specifically, but in the 1800s definitely were wrestling with that. The second major thing that was on the minds of physicists at this time was electromagnetic waves had been discovered and quantified to a great degree. We had Maxwell's equations and a lot of other field theories going on there. And the concept of the speed of light, speed c, was something that was being dealt with regularly. We had confirmed that. But the question was speed c relative to what? If you're driving a car at 60 miles an hour, you're going 60 miles an hour relative to the Earth. Okay, but if light going 186,000 miles per second, is that relative to the Earth? Is it the same speed relative to space? Is it the speed relative to the sun? Physicists were just kind of struggling with that, okay? And then the third major breakthrough in physics, and which was dealing with a problem, was the aberration of starlight. And probably of all these things on the list, the group on the Zoom call here tonight is most familiar with that. And so basically, but you may hear about that under another term, but basically when you're looking at a star, of course, in a telescope, that star is not where your telescope is pointed. As you know, the star has moved on, or of course the Earth has rotated, and the light is coming from where the star was when the light was emitted, and so many light years away, and is striking your telescope. So we all know that the stars are in the location, and that was called the aberration of starlight. But the important part to physics of that was that it proved that the Earth was rotating separate from space, okay? So physicists were glad to know that. They said, hey, this is great news. At least we know one thing now, okay? So the next thing that was a big event, it doesn't get as much attention, but it was a discovery by an Irish physicist that most of you probably never heard of, Joseph Lamore. But he discovered that the length contraction of objects in motion. What we mean by that is he discovered that particles moving through space flatten out as they increase speed, and they flatten out as they approach the speed of light. And so we won't go into any detail on this, but this was the equation that he defined, later became known as the Lorentz factor, and that was the amount of contraction that occurred to these particles, okay? So now we're going to park that for just a moment, that equation, move on to the Michelson-Morley experiment. Okay, this was an experiment, one of the most famous ones in physics, where they were trying to prove the aberration of starlight, because the concept there was, if the Earth is moving separate from space, then when the Earth is moving the opposite direction of space, there should be an ether wind blowing past the Earth. Space should be blowing past. And so if you had a light beam that was pointed in the direction that the opposite direction the Earth was moving, that it would go at one speed because it's going with space. And then if you pointed it the other direction, going against the grain or the flow of space, that it would slow down, okay? So that made total sense. They designed an experiment, Cleveland, Ohio, I think 1895 or so, and they split a light beam in half, bounced it off some mirrors, brought it back together, and then the waves come back together, they're in sync, and then they rotated the experiment around 360 degrees over an entire year. And what they expected to see was, as they rotated the experiment, the light waves would get out of sync, and they would have exhibit what's called fringe shift. Well, to their shock, there was no change in any direction at any time. Never did the light change at all. What this meant was that light, no matter what direction you're measuring it from, what perspective, it meant that light was traveling at the exact same speed. Well, this was the opposite of aberration of starlight finding. And this kind of implied that the Earth rotates the space around it with it, which doesn't make any sense. And physicists were baffled by this. And interestingly, the amount of error that it should have, the equation that explained the error of this was, guess what? A derivative of the Lorentz factor equation. So this really baffled physicists that were aware of this finding from length contraction. And so all these things are swimming around in physicists' minds at the time. And then here comes along the young Einstein. Okay, so Einstein has a train clock and light thought experiment that he's doing. And I'm going to go ahead and tell you the spoiler, and then I'll show you how it occurred. But to no surprise here, Einstein is going to do a thought experiment. He runs into a problem, and guess what? The problem is solved by this equation in a really strange way. Now, most people that study time dilation don't realize the background of all these things come down to this equation. So we're going to now take a look at Einstein's experiment and see what was on his mind. Now, this is there are 3 diagrams here. I've made them as simple as I know how to do, and they're actually very, very simple. I think that you'll be able to follow quite easily along this. And some of you remember this from your college classes probably. But okay, so what we have here is we have a train car, and we have a person here, person A. We have a light beam here, okay, and a clock. And so this person on the train is going to shine a light beam up to this mirror at the top of the train, and the light's going to come back down, and they're going to measure the speed of light, okay? Now, we presume they're going to get 186,000 miles per second, okay? So they do the experiment, and sure enough, it's 186,000 miles per second. Okay, so then we say, well, let's make this a little more interesting. All right, what we're going to do, and I'm going to go down here, actually put on a laser pointer, make it easier for you to track with me here. Okay, we're going to now take this exact same setup. I'll remove the train body here just to make less busyness in the diagram, but otherwise it's exactly the same train. We're going to give it a little velocity here, velocity greater than 0. So this train is simply going to come past us, and we're going to sit on a bank nearby with our own clock, and we're going to measure the speed of light also. So here's what happens when the train is over here. This gentleman hits the button, the light beam goes up, it comes back down, and the experiment is over. Now remember, when the train is over here, he hits the light button, the train and the light's going up all the way through his journey, and let's say that it stops right here, the light has made that full journey. Well, to the person inside the train, Einstein realized the light beam goes up and goes down just like it did over here, okay? And this is like if you're in a car and you're going 60 miles an hour down the expressway and you have a tennis ball in your hand, if you toss it up, it comes right back down to your hand. It doesn't, just fly off into the back seat. So that's because the motion is uniform, okay? And the tennis ball is going 60 miles an hour as well. That's why it doesn't do anything weird. Okay, so if this person is unaware of their motion, they will see the light beam go up and come right back down, and they'll measure the speed of light, and they'll say, yes, 186,000 miles per second, life is good. This person will say, well, let's see, I saw the light beam travel this distance, and yep, 186,000 miles per second. And Einstein, when he realized that both of these observers would come to the conclusion that light was 186,000 miles per second, he was totally baffled by that. Because you know this is true because we know that the light beam will make that sort of path. And that's, if you can't envision that, think about it this way. Imagine that all the lights are turned off in this train and it's dark, and this person has a glow-in-the-dark tennis ball, and they toss it up and it comes right back down. Okay, we know that'll happen. And if you're on the bank looking at it, you will see the glow-in-the-dark tennis ball will make a path like that. So the tennis ball or the light beam does travel this entire distance. So the baffling thing to Einstein was, how in the world can this observer say the light beam only went this far and declare the speed, 186,000 miles per second, and this observer see the light beam go a greater distance and declare the same thing, because the equation for velocity equals distance over time. They'll use the same equation. How can this be? Well, there's a mathematical derivation of this using Pythagorean theorem. Too much for this forum today. But if you run it through that, Einstein did, and of course he came up with a portion of really this formula. And he was pondering this. He said, you know what? If I take the amount of time that passes on this guy's clock and I multiply it by this factor, it solves this problem. And that tells me what time but what that says is that this guy's clock has passed more slowly than this guy's clock. And Einstein was completely baffled by that. So as he was thinking about this, he said, you know what? It has to be, the only thing that changes in this equation is the V. This is 1 divided by the square root of 1 minus V squared, the velocity of the train, divided by C squared, or the square of light speed squared, okay? So light speed is the same, theoretically. We're dealing with the law, relativity here, which argues that light is a constant. So this doesn't change in this whole scenario here. So the V is the only thing that's changing, but guess what? It changes the time. And so that's how he came to the conclusion that velocity must be changing time that is experienced by this person as reflected by the clock. The clock is just a measurement of that time. Well, so that's how Einstein came to the conclusion that time is warping in time dilation. Okay, so now let's move on to, with that in mind, let's go to the next example, the twin paradox. So if you take that concept that time is warping when you're moving through space, we have this very cool drawings here that Steve and his daughter did as well. We have Steve here, Steve's twin, and Steve and his twin have agreed that his twin, of course, is going to take the risk and go on the rocket ship. And the twin is going to go for a long ride, high rate of speed, forget about gravity for a moment, and then come back to the Earth many, many years later. And the twin has crashed the rocket ship here. You'll notice that when the twin looked out the window, so anxious to see his twin brother, only to see that Steve has aged dramatically when the twin has not aged anywhere near as much. Okay, this for most people is one of the most baffling things of time dilation. Now, when physicists explain this, they typically say that this person, the twin, the traveling twin, has traveled into this person's future. But that's really not true. If you think about it, this moment in time is this person's present, okay? And it's also this person's present. The equation does not have a reverse direction. Velocity is always positive, okay? Velocity, so therefore, velocity slows down time. It doesn't speed it up, okay? So what has happened in reality is this person's clock has simply slowed down, according to Einstein, okay? And I'm giving a little different definition by saying you don't travel into someone else's future. You simply slow down your own time, okay? And your present is the same for both. Now, the strange thing is it may be actually true that this person's body is actually younger than this person when that occurs. That's not been proven yet, but it actually could be the case. Don't know if we'll know that someday or not, but I'm going to talk about problems with time dilation here in a minute. But what Einstein's theory says is that this person's entire universe, basically his own existence, his frame of reference, the clock, the time, the passage of time slows down for this individual. Whether that's metabolism or whatever, is yet to be determined. But anyway, so that's the twin paradox. And now, at this point in time, when I was on my exploration for understanding this, I was baffled. I had done lots of research. I even understood that mathematical equation. I went through the problems of physics, the history and everything. And my quest was only to understand it. Well, at this point in time, I know a lot more about time dilation, but I still have no idea how can time warp. Okay, so I thought, okay, let me go into all these other experiments that were done, and maybe I can discover it that way. So here's a quick list of experiments that were done. I won't go into any detail on any of those, but just a quick tickler for you there. Einstein predicted that light waves will experience the transverse Doppler shift. That was found to be true in 1938. He predicted light waves will experience gravitational redshift near a massive body. That was proven in the 50s. Atomic clocks. Now, this wasn't a prediction of Einstein's, but the principle that he stated would make this prediction, that atomic clocks experiencing velocity relative to an at-rest clock will run slower, just like any clock, and they'll do it per that Lorentz factor, okay? And that was proven in 1971, famous Half-Lake-Keating experiment where they flew atomic clocks around in airplanes, okay? And Einstein's theory was very accurate into the billionths of a second, just shockingly accurate. Muon decay. Well, it was discovered that particles were decaying at a rate when they came closer to the Earth that was slowing down according to Einstein's theory, shockingly close to his mathematical predictions, even though he didn't predict that. And that gave further evidence of time dilation was accurate. And then the last thing that I needed to know was that Einstein's theories related to relativity are usually talked about as the most experimentally proven theories in physics. Okay, so I'm struggling at this point in my journey, saying, okay, I know it's true. It has to be true. All these experiments, the mathematical background, the history, the proof, it's just got to be true. But why can't I understand how time warps? Okay, and so what happened at this point is I said, okay, let me take one of those experiments and dive into it more deeply. The atomic clock. Okay, an atomic clock is not that different than your wristwatch clock. Okay, and so what I show here is I created a problem for myself, saying, okay, if I have an atomic clock, I called it the atomic clock problem. What changes in the moving clock that causes a shift in time? Okay, that was my experimental postulate there, my question. What I mean by that is, pretend for a moment, this is clock A, this blue here. Clock A, it's at rest, okay, on the Earth. And this is clock B in motion relative to A. So this is the clock we're going to take up in the airplane, okay? And we know in the end of the experiment that Einstein's going to be right, and the digital readout is going to be different. You see, this one says 2.12 bazillion, and this one says 1.919 bazillion, okay? We know that's going to read differently, and we can calculate exactly the difference there. And then we say time warped and time caused that. And I came along and said, well, okay, that's fine, but this readout is physical. The two changes by physical electrical pulse. I want to know how Father Time comes in here and changes this. Okay, is it magic? Does the electrode warp? I mean, what causes it? It's got to be physical because it doesn't make sense otherwise. So I took the drawing of an atomic clock there, and I won't bore you with this other than real quickly explain. There's an oscillating ion. There's an electron bouncing back and forth in an atom, usually a cesium atom. Okay, it kicks out a photon as it oscillates. Each time it oscillates, quartz crystal picks up that photon. When it does, it converts that into electrical pulse. The pulse is received by a receiver, translated into a signal, divided by 9.2 billion hertz, and then a second is declared, or a billionth of a second, whatever, on the clock. So it's actually pretty straightforward. Difficult to construct one, but pretty straightforward on what happens in an atomic clock. So my question was, something in here is changing to make that digital readout change. I have to believe that. I don't believe it magically just warps, you know. So that was my diving into that. So before I could even figure that out, even more problems arose for me. One was that I realized that time is not physical, so why would it be subject to laws of physics? Okay, time is a concept. We as humans give time a definition. We decide how long a second is, you know. And so, I struggle with that. And then on the reverse of that, clocks are physical and are subject to laws of physics. So their components must be affected by relative velocity of gravity. An atomic clock has to be affected. Now, maybe you could argue that maybe the velocity effect on an atomic clock is not enough to change anything, and it still warps in time. Okay, you could argue that, but I would say if that's true, I need you to prove to me that the components in the clock, the inertia of those components is not involved in the physical movement of the atomic clock before you can draw that conclusion, okay? And then the kicker for me was that neither of these issues was addressed in the theory or the experiments that I could find, not in Einstein's papers. Now his was the groundbreaking theory, so I didn't really expect to find it there, but in all the other explorations after, I couldn't find it. Well, at this point in time, I've got a dilemma. I'm really struggling because I've got all these logical problems that are coming around as I try to understand it, yet I've got, complete experimental proof that it must be true. And so I went through agonizing period of time here because I just wanted to understand how time warps. I didn't really mean to go through this whole, hundreds of hours of research and everything. But then, and I also I thought, well, I've seen all the DVDs I can see. I've bought books, research articles. I've, read all the experiments. I've dove in as far as I can, and I need to talk to a physicist, but I've already seen 25 physicists on video, and everything. And I was like, I don't know if I'm going to find that, but I need to talk to somebody. But I was too embarrassed. I really was, because I thought, I'm not smart enough to figure it out. That's the conclusion. Okay. And it's okay. Sell it in your heart, Jed. It's okay. You can't know everything. That's okay. But what bothered me was that I wasn't feeling like I couldn't understand it, because I thought, I was able to get along with the math. I was able to get my way through the theory. But what was bothering me was these logical problems. But I felt too embarrassed to go to a physicist and say that Einstein might have made a mistake. It's kind of hard tonight to even say those words, because I feel it's sort of disrespectful or heretical to this, the science I love and revere so deeply. And I'm like the biggest Einstein fan on the planet, and who am I to say this? I'm not even a physicist. But eventually I said, okay, I'm not going to figure this out unless I allow myself to just go ahead and pretend that maybe there is a problem, okay? And allow myself to go down that logical path and see where it leads. And then maybe I'll understand it finally there through that method. So I said, okay, I'm going to pretend that there's a problem. I'm going to go down that path and research it. Fast forwarding a few years, I actually did find what I believe is a problem in the theory. And I've got a theory that explains that. I'll talk to you about it in a moment. But I asked Steve at this point, I said, Steve, in the presentation, I needed a little bit of attention relief. It's gotten a little theoretical here. I need a pictorial way to segue into my theory that's really going to capture the essence of what I'm going to experience when I introduce my theory. And so Steve came up with this graphic, okay? And now for something completely different, okay? Basically, this is Jed roasted on a spit, okay? So, Steve, I gotta get a hand to, you can pack a lot of logic and a great point into a very concise message here. And this is exactly what I did experience once I started feeling around with some physicists and emails and things like that, saying that Einstein special relativity may have an error in it. And so Steve, you were dead right on that one. But I persisted nonetheless. And so we're introducing here atomic dilation, okay? And, if Einstein was on the Zoom call tonight and you looked at his little picture in the corner, that's exactly what he would look like, okay? He would be sticking his tongue out, I'm convinced, saying, Jed, let me sit down with you and let me explain it to you, and I wish he was here to do that. But anyway, so let me press on, and I'll tell you what the theory is and see what you think about it. So, okay. Forgive me for this longer definition here. It's expressed in scientific terms, but I'll explain it in simple terms. Okay, atomic dilation states that in an atomic clock, time dilation is not caused by the warpage of time, rather by the effect of relative velocity or gravity on the oscillating ion. Remember from that atomic clock earlier, the oscillating ion is what starts the whole process. And the effect on that ion causing it to track time more slowly. What I'm saying there is when the atomic clock is set in motion, the ion starts vibrating more slowly, and I'll explain why in a moment. Well, this gives the false appearance of time dilation. The same conclusion can be extrapolated to all clocks of all types. And so I'm saying that if it's a light clock, if it's a muon particle, anything like that, I'm saying that the effect is physical. It's not the warpage of time. The summary of that is, the bottom line is the math is correct, but the conclusion is incorrect. And let me give an example of this. Okay, if I said to everybody on the phone, hey, tomorrow morning, I predict it's going to be 32 degrees outside of my garage. And the way I know that is my kids leave the refrigerator door open every Saturday night. Okay. And so the next morning, I wake up, it's 32 degrees, and I say, there you go, okay? Well, there's two things. scientists have to remember that number one, you make a prediction and then you test that prediction. But number two is there are independent variables and dependent variables in any experiment. And if you're making a declaration of the conclusion, you also have to prove that the independent variable you're claiming caused the effect, in fact, did that. And you do that by isolating other variables and things like that. And so when I realized that all the experiments only tested the math behind Einstein's predictions and to greater and greater accuracy, I realized they had skipped that other scientific step of verifying that the conclusion was correct, that clocks, are or not affected by the motion through space. And again, clocks are physical. They should be affected somehow, some way, maybe not enough to draw a conclusion. Maybe it is time warping, but we have to eliminate those variables. And that gave me a little more confidence that maybe there was a gap in the theory there. And so I pressed on. So I'm saying that the math is correct, but the conclusion is incorrect in my theory. Now, let me explain why. Okay. So this is a diagram of an atom, a smaller atom and a larger atom. And I'll spend a little bit of time on this. This is the nucleus of the atom. This atom is velocity 0, so it's sitting there. It's the rest atom. Okay. Outside the nucleus, we have our electron. There's the dark blue path here is the low energy orbit of the electron. And the dotted blue path here is the high energy orbit. Many people don't know that when an atom gets stimulated, the electron bounces back and forth between these two energy states. Okay, I show that bouncing back and forth by the red wave path here. And when the ion, the electron, goes down, gives up its energy and bounces down to the lower orbit, it kicks out a photon. Okay, that's that photon generation that I talked about earlier in the atomic clock. So that's really how it does. It just vibrates back and forth, kicks out photons every cycle, and then we count those cycles. Okay, here's exactly the same atom, only it looks swollen. Okay, this is best thought of a bug splattering on a windshield. Okay, all right. What I'm saying here is this atom has velocity greater than 0. So we've given this atom some velocity. And you may remember that earlier I said, remember that Irish physicist in a very early presentation discovered that a particle going through space flattens in the direction of motion. Okay, my theory states that we know that's true. We know it does it to the Lorentz formula. And so I'm saying this is what the atom looks like from the front. Okay, from the side, it squishes like a biscuit. But from the front, this is what it looks like. Each of the orbits expand. And the expansion rate, I was able to show, I didn't go through the mathematics here that I have in my paper, but I was able to show that mathematically that expansion rate is according to the Lorentz factor equation. Okay, so what that means is, and I hope that was clear to you. If it wasn't, let's go back to the easier to understand atomic clock. Okay, so what I'm saying is that this was the clock we saw earlier. This is the clock at rest. These are the steps of the atomic clock and the final readout. This moving clock, clock B, what's happened here is you'll notice this photon, this has a higher frequency and this one has a lower frequency. Okay, the wavelength has increased when the frequency decreases. Okay, what I'm saying is when this clock is in motion, the atom spreads out or dilates, causing the length, go back here for a moment, causing the path that the electron takes to be longer, which takes it longer between cycles of kicking out a photon. All right. When that happens, then everything else performs like it normally does, but you have fewer photon signals going to here. Thus, in the end, you have a shorter readout. And this explains physically how an atomic clock in motion could generate this lower digital readout. To me, when I finished this, I was elated because it was so much more satisfying of an answer. It doesn't violate any of the special relativity principles, except it disagrees with the conclusion that was drawn related to time warping. Okay, now let's pause for a second. And once I got to this point, I then said, okay, let me go try to find an organization that will help me test this. And so I looked around, and lo and behold, I found that a few years earlier than I had come up with this theory, an aluminum ion clock had been used by the NIST laboratory in Boulder, Colorado, that was used to test relativity, and they were trying to make a more accurate clock than the normal cesium atom clock. They used a portion of a device like this on the right side called a Paul trap. This is a tiny device. I think it's about the size of a quarter. And inside this is a trapped ion that's oscillating. Okay, amazingly complex device inside here, but I thought you'd be fascinated by the design there, how they do that. But anyway, they detected velocity time dilation as slow of a speed as 10 meters per second, which is about the speed that a child does in a swing. Okay, that was remarkable. Excuse me. Okay, these experiments verified Einstein's prediction, the mathematical prediction, to 17 decimal places. It was a set a record beyond comprehension, just amazing. However, virtually all of the time dilation was caused by the ion frequency shift. Yet they attributed it to time dilation. Okay. Pause just a moment. Okay, I'll let that sink in. So what happened here was the frequency shift was physical, and it was recorded in the data of this experiment, and it matched the time dilation. So I was excited about this. I reached out to the organization. We've had a couple of conversations. They're willing to take another look at that, but I've got to have some credibility with me. I've got to have a physicist or an organization that goes with me to have that conversation, which I totally get, but I was excited to even get that far. Okay, so now here's the last slide I have before Q&A. So you can take a deep breath, relax a little bit. And so the status of my theory is that there were 20 hurdles remaining when I first realized that I might have something there. If the theory is correct, each of those has to be explained and modified, okay, because a whole bunch of conclusions have been drawn by special relativity. We're going to have to unravel a bunch of those. That's a pretty daunting task. However, over the subsequent years and months, for 13 of those 20, I've identified either a solution or a highly plausible theory. And interestingly and encouragingly, no showstoppers have arisen yet, okay? And that's very encouraging that I was able to solve a number of other problems. Now that I have this new definition, I've got actually a new definition of time and a new definition of what's physically going on. And so then when you apply that to some of those real complex things that are really weird, it explains it fairly quickly. So that was really encouraging too. And currently I am in active discussions with a physicist from a prominent university. We've had 6 meetings thus far. He's not kicked me out of his office yet. He got close a couple times, but he's invited me back. So that's good. So my next step goals are to finish those 20 hurdles. I've got 7 more to go, to either discover an error in the theory, and I'm still, assuming there could be an error, or to have a strong enough case that to be able to justify additional experimentation and expanded peer review. So basically what I will do, if I make it this far, I will have the physicist I'm working with or whoever ends up being brave or crazy enough to go along with me on this to design an experiment and go to the larger scientific community and see what we can do from there. So that's the status of it. Now, so at this point, I'll turn it over to Q&A. Hopefully there's at least one person still awake. And let me, it's probably best for me to unshare my screen here so you guys can raise your hands or whatever, anybody has a question. So any questions or thoughts?
Anybody have any questions for Jed?
Yeah, I have a question. Oh, sorry.
No.
You first.
Nope.
Great. I guess going back to your diagram of atom A and atom B, and you mentioned that you were kind of expanding kind of the orbit structure of the electrons. I guess my question is, you were kind of talking about how length contraction was causing this expansion of the orbit structure. So why would length contraction cause the atom to expand rather than actually contract and be a shorter path?
Okay, that's a great question. I'm going to use a balloon to demonstrate that, if I may, really quick. Okay, so we have a balloon. Can you see that on the? Let me see.
You better turn
Actually,
off
it turns invisible with your background.
Okay,
turn off
there
your
you go.
background, Jed.
Okay. Okay, how's that?
Good.
Fantastic. Okay, so here's the particle going through space. As it goes through, it flattens out like this, because that's pretty straightforward. It's contracting in the direction of motion. But if you'll notice, I've drawn that same drawing very poorly, but however, on the front of my particle, the energy state, energy orbits. Okay, watch what happens when I push it from the rear. It's just a demonstration. It expands. Okay, because if you think about it visually, this turns into like a biscuit. If you turn it around and we're able to look at it, if you took a piece of glass, and the reason I'm not doing this now, if you take a piece of glass and do that, the problem is when you turn it, the glass friction against the rubber doesn't allow it to expand. But I'm simulating the thing getting smaller, or rather more spheroidal shaped, and you can see that it expands in the direction of motion. All aspects of it expand. Okay, so just a theory. Is it true or not? Don't know, but that's one way I came to that conclusion. And the other thing was the gentleman Lamore, the physicist, had said that a particle does expand in the direction of motion, and it does to the Lorentz factor. Now, I'll say the final thing I'll say on this is that I don't know for sure if it is exactly what I am saying it is, but we can come to it from both ends, like a bookends. Number one is the physicist in the 1800s said particles they contract in the direction of motion to this equation. And then on the other end, we saw that in the NIST lab experiments that the ion in motion, the wavelength did increase, frequency decrease, exactly like I was saying. That means if wavelength increases, it had to expand. Okay. Now, whether it expanded exactly the way I say it does or not is yet to be determined. But so it's not proof, but there's two pieces of evidence that lead me to believe that it could be accurate.
Okay. I think I'm getting what you're saying. So I guess just as a follow-up then, now that you explained that portion of it, so what your thought process is that length contraction in one direction, in the direction of motion of the particle, is going to cause inherently length expansion in all other directions because there's some conservation of volume that you're trying to take into account. Is that the idea?
That's correct. That's right. Mm-hmm.
Interesting. Okay.
I believe James N., you have your hand raised. James, did you have a question? Okay, anybody else? Does anybody else have any questions?
Yeah, I do. Jeremy, this is Rick, and I'm stuck on the expanded orbit of the electrons in the cesium shell, and that when you say wavelengths increases, I mean you can't actually measure the wavelengths. They can't be measured. But what can be measured is the frequency, and the assumption is the wavelength increases, right? But the frequency is a time thing, right?
Frequency and wavelength are inverse of each other. So right. If the frequency decreases, wavelength increases. Okay, so that's correct. So what happened in the ion, in the National Institute of Standards and Technology experiment with their atomic clocks, they use what's called a frequency comb. I don't know if anybody's heard of that, but if you imagine my fingers as the waves, okay, what happens is when they measure the time gap between the two waves, okay, and those are very consistent. Well, that's an atom at rest. When the atom is under velocity, it actually goes like this. Okay, if you can see that expands. This frequency, it's like a comb, okay? The distance between the tines of the comb spread out, okay? And so when that occurs, the frequency decreases and the wavelength increases, okay? And so that's what they found. Now they only talk about the time gap between here. They're not talking about it being a physical effect on time dilation. They're just making the assumption that is what time dilation is. But so does that help any, Rick, that wavelength does expand and the frequency decreases?
Oh, not really, but it's probably just because I don't understand. Wavelength is a length measurement. It has nothing to do with time, right? But frequency is a time-based measurement. So a wavelength is a linear dimension.
It is a dimension, but remember that in the case of space or an electron bouncing between energy states, the distance it has to go will result in greater time.
No, I get that, but I'm saying you can't measure that. You can't measure that independently of time.
Hey, Jed, I can jump in here and potentially help this part of it. So
thank you.
Yeah. So if we all accept that the speed of light is constant, and we know that light comes in waves, and those waves have both a frequency and a wavelength, right? Well, because the velocity is constant and they're related to each other in that the frequency times the wavelength always equals the speed of light. If you know one, you always know the other. So that's why if you ever look at a light spectrum graph, like you can find one just on Google, you'll find that there's two axes that are both provided on this linear graph, one being frequency, one being wavelength, and they each have corresponding items. Like you can say red light is, I think, 700 or something nanometers. You can also provide that same photon or same wave in the form of a frequency measurement in hertz or megahertz, as it were, or maybe more than that. So in the case of light, where you know that the velocity of the wave in question is constant, the frequency and the wavelength are actually inversely proportional, and you can just calculate one if you have the other, in this case.
I have a question here that I think is relevant. So you're talking about electromagnetic radiation, where we have this connection between wavelength and frequency because the speed of light is constant. But Jed, you're talking about electrons in orbitals or in an atom. They are not electromagnetic radiation. So I don't think you can say there's this relationship between wavelength and frequency. And my second question, you're talking about the electron as if it's orbiting in the plane of the expanded dimension. So you're showing it as sort of a two-dimensional orbit, but really the electron orbits in three dimensions. And some of those dimensions are contracted and some of those dimensions are dilated. So that's where I start to lose your idea of how this fits together. How can you say that you have this expansion of the wavelength when the orbit is actually in all three dimensions, some of which are contracted?
The basic thought behind that is that it really doesn't matter. You're right about the orbit, but if you think about it, an electron is only in one position at any point in time. So its actual orbit is always a single plane. If you looked at after it orbits for a long period of time, it describes a three-dimensional space, but it actually only orbits at any moment in time in a single plane. So that's why I presented it that way.
Yeah. Can I ask a follow-up question to that? Because I do like this line of questioning, actually. And I don't want to be the one to drop quantum mechanics into the discussion that's already potentially too math for a lot of the,
By all means, go ahead.
But the idea that electrons orbit at all, and the idea that electrons are ever only in one place at a time is fundamentally counter to quantum theory. And quantum theory is one thing that's worth mentioning, is the other most tested theory in physics and independently verified to extreme levels of precision as well. And so trying to use quantum mechanical effects to justify a relativity discussion, at the moment, those two theories are not well compatible at these types of discussions, which is one of the biggest areas of physics that remains kind of unanswered to this time, and one of the biggest problems in our current understanding of kind of physics and a theory of everything. But kind of trying to squish them together into a theory where you're assuming an electron is in just one place at any given moment kind of gives me pause. I'll just start there.
Well, that's a great point. That's a great point. Anybody want to comment on that?
Well, correct me if I'm wrong, but in the realm of quantum mechanics, an electron or any quantum particle for that matter is sort of nebulous in terms of its location. We can only describe it in terms of a series of probabilities, if you will. It could be here, it could be here. However, when you do a measurement, then the wave function collapses and essentially becomes a particle. In other words, we know where it is, or at least with some degree of certainty, we know where it is once we measure it. So I guess that's where I'm kind of scratching my head a little bit as far as how testable a theory is when you're trying to get down to the quantum level of an effect like time dilation, because the measurement actually affects the phenomenon in the realm of quantum mechanics. So that's why it's so hard to measure, because nothing really is until it's perceived. So the electron is here once we measure it, but it's kind of a cloud of probability before then. So that's where I'm trying to kind of resolve in my mind the idea of the theory versus the measurement to justify the theory, if you will, or to prove the theory, if you will. If that makes sense, what I'm saying.
I have kind of another just fun thing to think about. So you said your theory is applicable to all kinds of clocks. So if my twin and I both are wearing a Mickey Mouse watch, which is a mechanical watch with a spring, and my twin goes out into space for 40 years and comes back, you're trying to tell me that her age will be different when she comes back because her watch is misbehaving rather than time itself is actually contracting?
No, what I'm saying there, let me say it two different ways. What Einstein says is that her watch will be will have run more slowly, and she will be younger. Okay. What I'm saying is the watch will have run slower, but it's not because of time. It's because the springs and everything are going to operate differently because of inertia, the traveling through space at a high speed. Okay. Her body, however, may or may not be younger, because if you think about this, take a runner that's running on dry ground and say he runs, a distance of 4 seconds. And then you take that same ground and you cover it with maple syrup, and he puts out exactly the same energy. Well, he's going to cover that ground in slightly longer time because of the friction that his feet encounter as they stick to the ground. Well, the question is, do our bodies, the metabolism rate of our bodies, will it slow down? Will the aging process slow down because of the physical inertia that our cells are experiencing? That's the one difference that I would argue, that it's a question whether or not the person's body will be younger. And the answer is that only if the physical metabolism is slowed down. It really have nothing to do with time. Einstein, if he were here, or a physicist supporting the special relativity, would say that each cell has a clock, or your body has a biological clock, and that clock slows down, and that causes your aging process to go, okay, that's very plausible. But so I'm saying the only difference is, yes, the clock will slow down, but it's physical. And I don't know if the body will slow down or not. It depends upon whether that inertia has impact on the cells of the body and the aging process. Does that help?
So in essence, and maybe I'm jumping to conclusions, but in essence, you're saying time is a constant.
Yes.
And not tied to space.
That is correct. And I realize that's, flies in the face of quite a few things there. But if you think about it, if you go back to that train clock experiment that I showed earlier, the guy on the bank and the guy on the train, ask yourself this question. The guy on the train is unaware that he has motion, lateral motion. It's not accurate to declare his time as an accurate time. Okay, relativity says both parties declare their watch accurate and both are correct.
Right.
But that's not really true because the guy on the ground knows that there's additional velocity and thus additional inertia involved in that equation that the person on the train is unaware of. And that would argue that there may be an absolute reference frame or there may be an absolute time. I'll say it this way, the guy on the bank has a more reliable time than the one in the train. We know the one in the train is different. Could you say it's wrong? Well, it's ignoring lateral velocity. So it calls into question the clock on the train is what I'm saying.
So a clock that's sitting perfectly still in the universe is the most accurate clock, or is the real clock, the framework clock?
Again, the universe is not absolutely still, though. It's not only
How do you know?
expanding, but it's accelerating in its rate of expansion. So is there any?
Well, no,
stationary
hold on. If what he's saying about time is true, then a whole lot of other stuff backs up and needs to be thought through, because our understanding of all these light shifts and everything else that we base the idea that the universe is expanding on. I mean, I hadn't thought that one through yet, but there might be holes to be shot in that.
Yes, and now where the absolute time location is, I'm not sure. But yeah, but it does argue that
There is a background framework.
Yeah, that's correct. Mm-hmm.
I got to think that through a little bit more. A background framework and absolute time.
Mm-hmm.
Yeah, I don't know. I got to think that.
I've been down this whole path with time too. That was the thing when I got into astronomy and started looking at cosmology. One of the biggest questions that came up in my head was all this stuff about time and relativity and understanding all this. So I've spent the last 30 years trying to understand that, and it took me some years in the beginning to break away from that fundamental framework idea, and it's going to take me a minute to work my way back to it.
Yeah.
Hey Jed, I got a question for you.
Sure.
So you've brought up the twin paradox, which is kind of the time sort of paradox that comes out of special relativity. Have you, and I'm not necessarily certain I know the name of this paradox, but have you heard the thought experiment about the train traveling down the track, going through the tunnel in a mountain such that it just barely fits on either side of the mountain? And
yes.
Yeah, okay, you've heard that one. Great. So I guess I'll try to say this without a diagram. It's kind of hard, but for those of you on the call, basically imagine a train that's exactly the length of a tunnel going some fraction of the speed of light. As it passes through the tunnel, some observer that's kind of outside the mountain just watching the situation, two doors come down on either side of the tunnel, instantaneously blocking the exit and entrance. And they see the train is fine because it fits perfectly in the tunnel. Those doors come up immediately and the train passes, no problem. Those people that are on the train, however, due to length contraction, the mountain itself is shorter in the direction that they're traveling. And so those two doors also come down to them as well. But to them, the mountain is shorter, the doors are closer together, and the train must get hit by one of those doors. It has to happen, right? Because the mountain itself is shorter. And that's the paradox, right? Does the train get hit by these doors, or does the train neatly fit in between the two doors in this tunnel? And so Jed, if you're kind of if you're trying to imply that there's a universal correct clock, then that paradox kind of remains unsolved. And I can provide the explanation from a special relativity standpoint per Einstein, but I'm interested, and if people want to hear that, I can kind of do that as a kind of a comparative reason, but I'm interested in how your version of the theory solves that without changing time, if that makes sense. Because it's kind of, in this case, it's not just a clock that's messed up, it's the train either is or is not destroyed by these doors coming down on the train.
Mm-hmm. Okay, that I have not solved that one yet, Zach. That's a good question. That's one of 7 remaining questions there, so I don't have a solution.
Gotcha. Okay. Is it question. Okay? I don't want to hijack anything. Is it worth providing the general relativity solution just as a comparative reason for those on the call, or should we just move on?
Well, I don't know about length contraction, so
I have a question, if I may.
Go ahead.
It's been a while since I saw this, but there were some experiments done here on Earth that were comparing the time near a mountain to time in distance away from the mountain. I wish I could find an example of that, but I can't at this time. But there was a noticeable difference. The clocks weren't moving, the people weren't moving, but the clocks compared from a distance closer to a large mass were slower than the ones that were in the distance away from a large mass. So what would your response to that be, Jed?
Okay, that goes back to the general relativity theory, and that was 10 years after Einstein's special relativity. What Einstein argued was that there's a thing called the equivalence principle, where gravitational mass equals inertial mass. Okay, what he means by that is velocity acts like gravity. Okay, so if you understand velocity time dilation, you're going to have the same effect if you move an object closer to a gravitational body. In other words, if it has a stronger gravitational field, that clock will experience the same slowing down as it will if it's experiencing higher velocity. Okay, so that explains if you take a clock to the top of a mountain, it has a lower gravitational field and the clock speeds up. If you take to the bottom of the mountain, the clock slows down because of the gravitational attraction on the Earth. Also, laterally, what you described was a clock that's not near another gravitational body like a mountain has more gravity. You know, that theoretically, if you're closer to a larger body and you have a sensitive enough clock, it would slow that clock down. So that's what I believe you're referring to there, and that's why they saw that effect.
So Jed, how would your theory kind of explain that? I think was where she was going with that.
Okay, my theory says that it's inertia, both for velocity and gravitation. That the equivalence principle kind of brings them both together. If inertial mass is the same thing as gravitational mass, then inertia is what's happening. The reason a clock, atomic clock or a Mickey Mouse wristwatch slows down when it's subject to velocity is the inertia that it experiences. Okay. Another way I would explain that is that, think about it, if you were going to set a clock, you would on the Earth, if you took a pendulum clock and you set it, for every arc stroke is a second, and then you took exact same clock to the moon, you would have to adjust it, right? Because the moon has a lower gravitational strength. The pendulum clock would go back and forth quicker. That's not because of time dilation. That's because of the gravitational field difference. So what I'm saying is that inertia, whenever you give a definition to time, the definition of a second, definition of a minute, billionth of a second, whatever, what you're actually doing is you're saying time is the measurement, it's a unit of measure of the consumption of motion in a given reference frame, okay? So if I say pendulum clock moves this far, one arc stroke, that equals 1 second. I have to say the pendulum clock moving one arc stroke equals 1 second at sea level on Earth. Because if I take that clock to the moon again, one arc stroke is not going to be equivalent to 1 second as I define it normally. So what I'm saying there, what's missing, and what bridges the gap between this is the fact that you have to declare the reference frame you're in, and inertia is the difference between the two. And that's why the gravitational time dilation and velocity time dilation have the same net effect. Does that help any there, Zach?
I'm sorry, what's that?
Does that help? Or does that...
Well, yeah, it wasn't my question. I
Okay,
forget who asked it originally.
Sorry about that. Yeah.
Yes, thank you for the explanation.
Okay.
I think we have a question here from Peter and Julia. You had your hand raised.
Yeah, I typed something in the chat. You might not have seen it. Thanks for the presentation. Very interesting. I'm not as up on the theory, but I'm kind of curious. Have you thought about what an practical experiment to test this might wind up looking like? You know, how can we actually check this box one way or the other?
Yes, we could do some, repeat the experiment that the NIST labs did with some plot twist to that. That's the fastest, easiest way to do that, because the experiment has already shown that wavelength does change, the clock changes there. So let's set it up with that intention in mind. Okay, they experimented for another reason there, happened to collect the data, and I was able to show, that data confirms this. So that's the first thing I would do, is repeat that experiment, different laboratory, maybe different setup, with that intention to actually answer the question, like the question posed by Ann or by Zach and others about the wavelength expansion, Rick, et cetera, and really study that. Does it really work that way? Does it really expand? The second thing is from a particle perspective. Physicists have done lots of experiments about the contraction direction of motion. Let's go back and find out, maybe measure something we haven't tried to measure before, is does it actually perform the way I describe it? The third one is, this one is a bit of a challenge to put together, but an electric motor clock spinning at really, really high speed. I was trying to figure out something that I could do reasonably without having a lot of money in a physics laboratory at my disposal. But a high-speed, high RPM motor with a disc and holes in it, a laser shooting through the holes and into a light receptor, and then having a control clock on the Earth at sea level and taking one at the top of Pikes Peak. Okay, and I've done I'm in the calculations now to see how sensitive it would have to be to do that. Pretty darn sensitive. I'm up over 100,000 RPMs and a lot of holes in this disc. Okay, to be able to do that. And the thought behind that is that if you're going to make a prediction, the clock will demonstrate so much time has passed by the number of the laser pulses going through there. But you'll be able to show that the laser passed through the pulse hole. Okay, that's physical. That's not warping of time. And so that's the concept behind that. I'm not finished designing that, but I was discussing that with a physicist recently, that was a possible thing. So those are three ideas that I'm toying with right now.
That last one, Jed, just out of curiosity, your thought is that laser going through these holes in the disk would not be subject to the expansion sort of situation that you were describing previously with kind of electron orbitals, and therefore would be not constrained by times changing at different elevations?
That's a great question, Zach. And here's the bizarre piece of this experiment. No matter how it turns out, it will confirm what I'm saying. Now that sounds bizarre, okay? What I mean by that, think about this. Okay, so if you set the clock up, the laser beam goes through there. When you're done with the experiment, whether the laser was affected by the gravitation or not, the readout of the clock is only determined by the number of holes that passed, okay? And so if the clock slows down, speeds up, if you take it up to Pikes Peak, it'll speed up. If the clock reads more time has passed, according to Einstein's theory, then you can say immediately after that, Einstein was correct about the math, but you know what? I counted exactly this many holes passing. It's physical, okay? If it doesn't speed up, then it should have, right? According to Einstein's theory. And then you say, well, wait a second, what happened? And then you say, well, remember inertia, okay? The shaft of this clock will, if at the top of Pikes Peak, the gravitational inertia is lower and the shaft should spin faster. We can calculate that in advance. And if it's a free spinning shaft, then it should, spin at a different rate. And so either way, I believe in the end, you'll have to say, you know what, this is physical, that we're demonstrating that time, the passage of time, the measurement of time, I should say, is physical. Okay.
I don't think an electric motor is going to get you there.
It's going to be tough. Yeah. The Swiss have a 1 million RPM motor.
Well, I know, but it's dependent on the rotation of the electromagnetic field.
Exactly. Very difficult, to do that. So I'm not holding all the hope on that one. So I'm back to the best way is that aluminum ion clock that already exists.
Yeah.
already functioning.
All right.
So kind of simplifying this and getting back to one of your earlier slides. You have two twins, okay? Maybe the scariest thing that you talked about in your presentation was the possibility that Steve Wright could have an identical twin out there. But let's just say hypothetically that that's true. So if Steve is in his car driving at 60 miles an hour and the windows are covered and he holds a tennis ball in his hand and he throws it up in the air, it takes 1 second for the tennis ball to come up and down. And again, the windows are blocked, so he has no sense of whether he's stationary or moving. As far as he's concerned, he's stationary. And your description of time being the path that a particle travels, a certain distance that it travels in a certain unit of time. It's a measurement. It's all relative. So if he tosses a tennis ball in his car, it goes up and down in 1 second, and this is the path, straight up and down. Now, Steve's twin is on the side of the road observing that same phenomenon. Let's say that the windows are no longer covered. As the car is moving, the tennis ball starts, it goes up, and then it falls down over a curved path, which is a longer path. And as far as his twin is concerned, the time that it takes is going to be longer because the path that it takes to follow is going to be longer. So it's relative. This is the concept of relativity, right? So where I'm 60 miles an hour is nothing, but of course, when you get up to a significant fraction of the speed of light, the effect is measurable. I guess where I'm struggling to try to wrap my mind around this is how does speed actually affect the clocks, the biological clocks, if you will, inside of the cells of Steve's twin so that he ages faster as a result of standing stationary on the side of the road relative to his motion in the car? How does motion actually affect the clocks in Steve's cells, causing him to age more slowly than his identical twin?
Okay, great point, great question. Okay, so on that one, my theory says that it may be that the twin does not change their age if they're, the theory, most physicists that you talk to in that regard will say that this body, the cells have biological clocks. Their clocks will slow down just like a muon particle's clock will slow down, okay? And all clocks, all measurements of time. So that's what they would argue. I would say, well, I'm not so sure because the passage of time may not be the trigger mechanism in a human cell. It may be chemical half-life, or it may be something else. So I stop short of saying that twin will actually be younger in my theory, okay? I'm saying that their wristwatch will definitely have gone slower and their body will have experienced more inertia. What that inertia will do to the body, I'm not so sure. And I think we get a glimpse of it when we're on an airplane, the jet lag. You're dragged through space at, 500-600 miles an hour, or whatever the speed is. And, for a couple hours there, you'd feel tired for some reason, It could be other things, but that may be one explanation of that. And the other thing I would say, Jeremy, back to your example of the car and the ball, the tennis ball, is think about this. If you said, which one is correct? Well, relativity says they're both correct. But actually, science has to say, no, the guy in the car is wrong. The ball really did travel that parabolic distance. It really did. The guy in the car just didn't know that. And that's a hard thing for me to get over because it's, I think it was Zach earlier talked about, a bit of simultaneity, that an electron's not in one spot. It, can be in more than one position at a time. That's true. Totally agree with that. The point is that, back to the car example, there is, in that particular case, those two reference frames one is more accurate than the other. You can't argue that. And that pushes us back to the absolute reference frame that Rick mentioned, okay? And now you get pulled back the other direction with other examples there, but that's hard to get over, that reference frame. The tennis ball is moving in a parabolic path. It traveled that distance. And actually, it traveled another parabolic path, okay? The Earth that the car was sitting on in that same time frame, it did another one. And now we're back to, somewhere in space, maybe it's Rick's backyard is where absolute time resides. I don't know. But
pretty sure it's not it.
He's aged considerably, so it can't be there.
Since this call started.
Hey, Jed, mind if I pose a quick reversal of the situation on you and see what you think?
Absolutely, yes.
So let's go back to the train with the tennis ball. In this case, well, let's make it a photon so it actually works though. But we can think of it as a tennis ball if you want. So the photon goes up, makes that weird pyramid path, like you said in your diagram, just like you said, and the person outside looks at the person inside's clock and it appears to be ticking slower. Well, let's give the person that's sitting on the shore or on the bank, like you said, let's give them an atomic clock as well with another photon bouncing up and down. Now let's put ourselves in the body of the person in the train, okay? They look out at this person on the bank and they see this guy passing by them because they don't feel the train moving, but they see their environment moving. So they look out and they see this other dude with their clock and they look at their photon and it makes that same pyramid path, but their clock makes just the pure up and down path like you were describing. And if you ask the person on the train, they would say, well, that dude was going at a relative velocity of pretty fast and his clock was going pretty darn slow. So both people look back at the other person and say the other one was going slower. And in the end, somebody has to be, once they meet back up, and this is kind of back to the twin paradox, once they meet back up, somebody has got to be right. Or, well, either somebody's right or they're both right. And how do you determine, which one is the preferred reference frame? And then on top of that, as a follow-up, like you mentioned the motion of the Earth, and you said that the parabola of the person in the car is actually a parabola. It's not straight up and down, right? And that's the true motion. But let's say that person's driving counter to the rotation of the Earth, and actually that ball is going slower than everything else on Earth. Your theory might say that, well, the aging process, whether or not the aging process happened, the clock is definitely reading slower. But, if you kind of zoom out, if you assume that there is a global reference frame that's absolute, actually that clock could have been moving slower than everybody else and therefore should have been faster, which would be the opposite result. So I guess what are your thoughts on that sort of aspect of it?
Good questions there. Okay, so I'll give you the punchline and then I'll back into it. Okay, the punchline is the clock that is moving the slowest is the reference clock and the accurate clock. Okay, how do I know that? Well, go back to the tennis ball example. Okay, let me give you another example. Relativity says, you're exactly right, Zach, that let's take two spaceships out there with nothing around them, and they're going towards each other with a closing velocity of 60 miles an hour. Well, this spaceship A says the other guy's going 60 miles an hour, and spaceship B says, no, I'm at rest, you're going 60 miles an hour. Relativity says there's no way to tell. But I'll give you an experiment that will refute that. If both spaceships leave and you program them to, on their clock, one of them is going 60 miles an hour, one's going 0. On their clock, you say every hour, shoot a light beam towards the other one. Okay, guess what? Eventually, after a little while, the light beams will not arrive at the same time. Okay, ship A will shoot its light beam. They're supposed to arrive 1 hour on the hour. Okay, and so the one with a slower clock is the one that has the greater velocity. And this is one of my 7 things also to run the math on, but I believe that you can calculate the lag in time on the receiving person's clock. You can reverse calculate that and you'll be able to say, no, rocket B is the one that's moving. And by the way, they're going 60 miles an hour, or B is going 45 miles an hour and A is going 15. I don't know that for sure that you can calculate that, but I will say that thought experiment does answer that question, that there is, you can tell that someone's moving or not. And as long as you can see both of their watches or their clocks, then you know that if your clock is slower, you have the greater velocity or you're exposed to the greater gravitational force. And therefore your reference frame is more accurate than the other one.
I just figured out which clock is the baseline clock.
The slowest one.
It's the one that's not moving in the Higgs field.
Okay, I can't
Because
comment on the Higgs field on that one. Rick.
because that's where the inertia comes from.
Yes, yes.
So motion through the Higgs field is what generates inertia.
Mhm.
Of course, that means it's got to be perfectly still, and when particles that we know of become perfectly still, they become, well, non-existent, right? What things that happen at absolute zero, they start to disappear.
Okay, engaging discussion. Does anybody have any other questions? We're kind of wrapping up here and toward the end of the time. So I'm going to watch the recording of this again. I'm going to come up with like another 15 to 20 questions. That's what's going to drive me nuts about this. I'm going to watch this again. It's going to stimulate something else. I'm sure somebody else is going to have the same experience. We're going to have a bunch of other questions. So in some ways, it's a little frustrating that they don't all come to mind right now. But what this really does is it gets you to kind of think through the process. And it's been maddening, of course, for the better part of a century. So,
Jed, it's been a wonderful discussion and good to hear your theory. I'm not sure I'm sold yet, but hang in there.
Yeah, I appreciate that.
Yeah, no, I echo the sentiment. Really appreciate you taking the time to present this to our group. I'll be curious to know the results of your interaction with I believe it's Purdue University, the professor that you're talking to.
Yes.
Okay. So yeah, keep us posted for sure on the outcome of this. It's a fascinating perception of this angle of this, if you will. So, and it will continue to stimulate a lot of thought.
Okay, thank you very much too. I really appreciate it. I really enjoyed it. Thank you for the great questions. I made a lot of notes as we went through here, and that's helped me as I develop it further. And yeah, I'll keep you posted on how things go. And I may be on the street. The next time I'm here, I may have a cardboard sign up needing some help or a place to live or whatever, who knows.
Hey, I'm happy to hear that Memphis is your true home. And when we get back to live meetings, if you're ever in town, please, by all means, pop into one of our meetings or one of our events. You're welcome anytime. You're part of the family as far as we're concerned. So,
well, thank you very much. I will certainly do that. I'd love to do that. Thank you.
Thanks again. Getting a lot of positive comments here in the chat on the discussion. This is one of the most engaging discussions that we've had in quite a while. So fantastic. As we wrap up here, just got a couple of announcements for everyone as we wrap up the meeting here. First of all, next month, for those of you who subscribe to Sky and Telescope magazine, if you got the March edition, you'll see that the cover features an article on Betelgeuse, which of course made the news a little over a year ago for actually the title of the article, which is The Great Dimming of Betelgeuse. So next month, our April meeting will feature the guy who wrote this article, Tom Calderwood. He'll be giving us a presentation on basically the article that he wrote in the March edition of Sky and Telescope on the Great Dimming of Betelgeuse. And that's going to be the second Friday in March, because the first Friday is, I believe, Good Friday. That's the Easter weekend. So I think the date is April 9, but
yeah, you
definitely want to April 8.
You mean you've been saying March.
Right. But the meeting is going to be in April. It's the March edition of Sky and Telescope. Correct.
There you go.
So March edition of Sky and Telescope, Great Dimming of Betelgeuse. He's going to be our presenter for the April meeting. And of course, we'll send out a formal announcement on that as well. So make sure you mark our calendars. That's going to be our next meeting. It's like 5 weeks from today, second Friday in
April 9th.
Yeah, April the 9th. That's it. So let me do a quick screen share here also, just to kind of wrap things up here. So, okay. And of course, these are our details. Our website again is memphisastro.org, and joinmas.com is where you go to join our email distribution list if you're not on it already. So be sure you check that out. And again, I will have links to these 2 documents. It's actually the March sky map and then also the membership application in the description below this video. And tomorrow night looks promising. So if you're on our email list and the weather's clear, we'll send out an announcement. Bring your telescope. Again, we're still being a little careful as we ride out the end of COVID, but many of us have had our vaccines or are in the process of getting vaccinated. So as we move through this, time to get back out again. So yeah, definitely check that out. And hopefully tomorrow night we can get out and do some astronomy for a change. So that is it. So again, I want to thank everyone for taking the time to join our meeting tonight. Thank you again to Jed for a great presentation, a lively discussion. If anybody has any other comments or questions, now's the time. Other than that, we will just wrap up. And again, wish everybody a happy month, happy week, happy weekend. I know we got spring break coming up. Weather's going to get nicer as we get into the spring months. We got some great programming coming up. So be sure you mark your calendars for that and keep an eye on your email. And with that, I will officially sign off and say, have a great night, everyone. And we'll see you next month.
See you next month. Thank you. Thank you, Jed.
Thank you. Thank you.
Jed.
Appreciate everybody.
Thank you. Good night.
Yeah, well done, Jed.
Thank you very much. Yeah.